Let's consider traveling longitudinal waves. Well, sound wave is a longitudinal wave. How do we describe sound wave? Before we learned about transverse wave, that the amplitude is around y direction and the propagation direction is around x direction. So we learned to describe it as that y equals to something associated with x and t. But this time it's longitudinal, which means that the amplitude is also along x direction, for example, at least parallel to the traveling direction. So we have to use different notation to describe it. And we use this S means displacement of the volume element from its equilibrium. If you still remember that along a thin long tube filled with fluid, if we cut a slice of it, well, each slice has its equilibrium position, which means undisturbed. When this slice starts to move away from its equilibrium position, the displacement we define as S, and X is the position of its original equilibrium position, and time is T. So how much the displacement of this volume element experienced can be described as Sm, that is a constant, times cosine kx minus omega t. This still follows the same definition as any traveling wave. Minus omega t means that this traveling wave moves left to the right along the x-axis, and k is the wave number, that is 2 pi divided by wavelength lambda, and omega is the angular frequency of 2 pi f, or 2 pi divided by the period of this wave. Now, we're going to learn something that a traveling longitudinal wave, its displacement actually is associated with the pressure difference. Because in our case, we say that the reason there is a sound wave is because the pressure difference. The sound wave is actually compressional waves. We learned this equation from chapter of 12. That is something that defined book modulus. And book modulus, as a matter of fact, equals negative of delta P, which is pressure difference, divided by the ratio of change of volume over volume. Now we just changed to another format. Now we'll start from here. Well, if we assume that at a undisturbed zone, the pressure is P of O, and we cut a slice of moving fluid at thickness of delta x, and then the cross-section area, since is A, then the original volume, let's define as V, suppose equals to that cross-section area A times the slice delta x we cut. And this is at the regular pressure zone. At any other place, let's say a compression zone, pressure is PO plus delta P. That is the change of the pressure, for example. And therefore, due to the change of pressure, that this slice of moving fluid will change its thickness. How much is changed, as a matter of fact, is delta S. Why? Because that is the displacement difference between the leading edge and also the trailing edge. So since this delta S is the change of the thickness, then the cross-section area still remain as A, then change of volume will equals to cross-section area A times the change of thickness. So if we replace this delta V with A delta S, and originally V as A delta of X, and we have a very interesting situation that delta, as a matter of fact, means change. And if we look at this, if we want to delta of this, which is displacement, it is associated with two variables, x and t. When that happens, we do not use the regular differential, which is dx or DES, we use partial differential. Well, therefore, we have negative book modulus, cross-section area A cancels, delta S become partial S, which means change. Delta X is partial X. This also means change of position, change of displacement. Now, mathematically, this will still be the same as you do differential of this with respect to change of X. So, if we consider because X change cause S change, then we view this T as a constant. Therefore, let's give a try. Partial S, which means change of this, equals to, this is obviously a constant. Cosine, when you differentiate it, will become negative sine. And then when you differentiate that against X, this K comes out. So it's negative of K of SM, cosine change to sine, of Kx minus omega t. Because when we differentiate this minus omega t, that is constant, therefore it's 0. This is a result of partial S, and then because it's against X, so we have a partial X right here. Therefore, we obtain the ratio of partial S over partial X, which is right here, over this. Now, if we replace that partial S over partial X as the result of our derivative of minus KSM and sine KX minus omega t, what we get is that negative cancels. We have book modulus and wave number, maximum displacement SS, M of sine of Kx minus omega t. And on the other hand, we just learned that book modulus is associated with speed of sound, which, if we remember, that is speed of sound equals to square root of book modulus over density of the fluid. So if we plug in this B, that is V squared rho. Therefore, we continue this equation. We plug in this B as V squared of density of the fluid, and we have K SM. If we define all this as the pressure amplitude, maximum pressure amplitude of, define this as delta P of M, and the rest of it is a sine wave, that's a traveling wave, sine of Kx minus omega t. So what we have left is change of pressure and equals delta Pm, that is just a bunch of constant we define as the pressure amplitude, and times sine of Kx minus omega t. This tells us, as a matter of fact, that sound wave, starting with a compressional displacement wave, now actually comes out as also a pressure wave. That a change of pressure of the fluid is associated with that the pressure amplitude time a sine function. It depends on its position and depends on its time. Sound wave, so therefore, sound wave may be considered as either a displacement wave or pressure wave. Now, what I also would like to point out is that the maximum displacement SM is very, very small. And therefore, sometimes in order to measure sound wave, we do not measure the change of displacement. And usually we will more prefer to measure the change of pressure. The reason why is that the SM is very, very small. It's almost not be able to noticeable. Let me give you an example problem. The maximum pressure variation delta Pm that the ear can tolerate in loud sound is about 28 Pascal at 1000 Hertz. So let's say the maximum of the pressure change an ear can be tolerate is 28 Pascal. That is the pressure, unit of pressure, and at frequency equals to 1000 of Hertz, which means that is associated with frequency. Now, the faintest sound that can be heard at 1000 Hertz has a pressure amplitude about 2.8 times 10 to the negative 5 Pascal. So the maximum is about 28 Pascal, and then the minimum is 2.8 times 10 to the negative of 5 of Pascal. So this is a case that by given the pressure difference for a signal at frequency of 1000 Hertz, obviously this is audible sound range, and to the threshold of pain, that is 28 Pascal for the maximum pressure change. For the faintest sound noticeable by the ear is this much, that is the minimum of delta PM. Now, let's use this data to calculate how much the SM is related for the biggest pressure change and for the smallest pressure change. Now, since we know that the wave number k is 2 pi over lambda, so we can calculate the wave number k by plugging the formula, because the frequency is given and speed of sound at room temperature, usually we use 343 of meter per second. So we know that wavelength is speed of wave times its frequency. So we can replace that by 2 pi, wavelength is speed of wave times the frequency. Okay, sorry, I should write the other way. Speed of wave is wavelength is time frequency. That's the way it should be written. Therefore, that wavelength is actually speed wave over frequency. In this case, it's that. So the frequency goes to the numerator, and we can calculate the wave number in this case. That is 6.28, which is 2 pi, and this f goes to the numerator. That is 1000 of hertz, and speed of sound here is 343 meters per second. Since we all use SI unit and we do not have to plug in a number, the result for k is 18.3 of radian per, well, as a matter of fact, this is in meter, so that's that. And then once we have this k, we can calculate SM. Why? Because that delta PM defined as V squared of rho and k and SM. So therefore, SM has a relationship with this delta PM, and the rest of it obviously is k, rho, and V squared. Now, density of the air at room temperature is around 1.28 of kilogram per cubic meter. Since we already solved the wave number k, we know the density of the air at room temperature, we know the speed of sound, 343 meters per second, and then we can plug in this for the maximum of pressure change, 28 Pascal, that is SI unit. Pascal is Newton per meter square, and we can find for the maximum SM. The result comes out as 1.1 times 10 to the negative 5 of meter. So this is very, very small. That is almost that 11 of micrometer. That is when the pressure amplitude is 28 Pascal. So you can imagine for the faintest sound that if we use 2.8 times 10 to the negative 5 for the pressure amplitude, then the SM for the minimum, which is the faintest sound situation, will come out even much smaller. So it is 1.1 of times 10 to the negative 11 of meter. This is 1/10 of the size of a usual atom. That is very, very small for displacement. So that's therefore it's very hard to measure the displacement of a sound wave. We more prefer to measure the change of its pressure.